Thank you for people that are here. So let me briefly introduce Jason Hartline, a great friend, researcher. After his PhD in Washington University, yes?
University of Washington.
University of Washington, it's not the same. In computer science. He was postdoc in Carnegie Mellon and Microsoft before joining Northwestern University. Now he's full professor at Northwestern University, and he's one of the leader of economics and computation community in the world. He spent 1 month here with us in Morocco. So all January, he was co-organizing this amazing winter school 1 week, last week, on data economics. And now he gives a lecture all this week on approximate mechanical design, amazing lecture. And we are very, very happy to have him with us today. So the floor is yours, Jason.
Great, thank you. It's been, is this on? Yes, it's on. It's been great to be here for the last month. Today, I'm going to be telling you about research on regulating algorithmic collusion. This is joint. We have 2 papers now. The first paper is with Sheng Long and Chenhao Zhang, and the second paper is with Cheng Wang and Chenhao Zhang. So regulating algorithmic collusion. There have been a number of economics papers talking about what might happen to prices if algorithms are setting prices, and observing that some of the algorithmic configurations lead to prices that look like they're super competitive. And so if that's happening, maybe this is concerning about the role of what happens when algorithms start taking a bigger and bigger role in our lives. And so this paper is going to look at, I think a question that's going to be increasingly important, which is what should regulators do about the increased role of algorithms in our lives, and how do we, think about sensible regulations so that algorithms don't lead to bad outcomes like higher than competitive prices in markets. Cool. So I want to have a very simple model of imperfect competition, imperfect price competition in mind. Okay, so I'm thinking about sellers in online markets that compete on prices, and online markets like Airbnb or eBay, where if you think about Airbnb hosts have a room. Each room is not the same. Some customers prefer to have a large kitchen with all the things you need to do cooking. Some customers prefer to, some users prefer to have a room that's very close to a street with nice cafes, and so all the rooms are different. So these sellers are going to be trying to maybe use algorithms to figure out what prices are going to give them the most profits in their Airbnb business. And they might like to use learning algorithms to optimize their prices. And so a central question here is, do these learning algorithms result in competitive prices, or do they result in prices that look kind of like collusions on higher than competitive prices? Or, for example, what if Airbnb was to recommend to the sellers, hey, figuring out good prices is hard. We'll give you an algorithm that's going to recommend prices to you, and if you take the recommendations, it will try to learn what good prices are. Okay, but if Airbnb is recommending the algorithm that all of the sellers in the marketplace looks like, that might look like, if it results in higher than competitive prices, it might look like price fixing on Airbnb's part. Okay, so there are a couple of perspectives we might take here. We might take the perspective of the regulator, who is worried about the marketplace being competitive and wants to have sensible legislation that helps make sure the marketplace stays competitive. Okay? we might worry about sellers. We might take the perspective of sellers, thinking, look, I'm selling in this marketplace, but I want to make sure that if I run an algorithm, it's not going to inadvertently collude with other algorithms to result in higher than competitive prices, which then mean I might get audited by a regulator who's going to then tell me I did a bad thing. Okay? And we might be taking the perspective of the platform like Airbnb, who's trying to provide an algorithm to all the Airbnb hosts. They're going to help it better optimize their prices. Okay, and Airbnb doesn't want to be then audited by the regulator that says, hey, you're price fixing in all the markets you're in. Cool. So here is a really simple model that you can just have in the back of your mind. This specific model is not all that important to us in the end of the day, but it's nice to have something concrete to think about. So the model I want you to think about is I just have two sellers, 1 and 2. Each seller has their own item. Okay, these are different items. So room 1 and room 2, different locations in the city. Okay, each seller has a cost for having someone book their room, and they're going to post a price. And our buyer is going to arrive. The buyer will have a value for each of the items, which might be different for the different items. And they're going to choose the item to maximize what they most prefer, the utility being the difference between their value for the item and the price for the item. Okay, standard model linear utility. Okay, so the timing here, the seller posts the price, the buyer arrives and buys a preferred item, if any. Okay, just to have a picture, here's my picture of my two sellers. Here I've drawn their costs, C1 for seller 1 and C2 for seller 2. So the joint costs are a point in two-dimensional space. Okay, they both post prices, P1 and P2, which are then a point in space, right? And a buyer is going to show up with a value here, which says, again, a two-dimensional value, the value for item 1, a value for item 2. Remember, item 1 is the room of seller 1, and item 2 is the room of seller 2. Okay, and then they make their decision based on which gives the most utility. Okay, so here, the utility for item 1 is the distance between V1 and P1, which is the length of that arrow. And the distance, the utility for item 2 is the length of this area, the distance between V2 and P2. So this buyer chooses to buy from seller 1, right? Because this arrow is longer. Okay, so to figure out what's going to happen, we draw a 45-degree line up from the price. And the people over here buy seller 1. The people over here buy seller 2. Okay, so what is the selling probability? Xi, the probability we buy from seller I, is the probability that the buyer's value is in the region AI, which is the region of buyers that will buy from seller I. Okay, and the payoff of the seller is what? The payoff gets a utility, which is the price offered minus the cost, so that's this difference, times the probability that the buyer is in that region. Cool, so that's like a basic model of imperfect price competition. Okay, so let's look at a very specific example of this. Let's imagine the buyer's values are uniformly distributed on 0, 1 for both sellers. So that's uniform on the square. Okay? Again, I have two sellers, and imagine their costs are 0.1 and 0.2 for sellers 1 and 2. Okay? Well, then you could solve for what the equilibrium prices are in this marketplace. Is that going to go away? You can sell for the equilibrium price in this marketplace. You're going to get prices of 0.5 and 0.55 as the equilibrium prices in this marketplace. Okay, one notable fact, like if you know about price competition, with imperfect price competition, prices are not going to be costs. They're not costs here. There is some sort of, revenue that the sellers extract. Okay? The sellers could collude on prices. And if they were to offer these collusive prices, which are basically 0.1 higher, so 0.6 and 0.66, 10% higher, 20% higher, they both get more revenue from this. So in my picture, this looks kind of like this. There were equilibrium prices in black, and then I have these collusive prices in purple. Both sellers make more money with these collusive prices, but there's a whole bunch of customers that don't buy anymore, and so we lose social welfare from the equilibrium prices. Yes, please.
Equilibrium price, how come you have seller one selling a lower price so that the buyer will always pick seller one?
That is not correct. No, so let's go back to my other picture.
That's V minus PI.
Right, so the buyer has a different value for both items.
Okay,
And the value for the items I plot in this two-dimensional plot.
I thought it's the same.
Yeah, and they choose the thing that maximizes value minus price. Cool. This is a good model to have in the back of your mind. The details of the model are not important for me. We're just going to not care about this after this slide. Okay, but you should be thinking about that in your back of your mind. Okay, so there have been a number of awesome econ papers exposing the potential harms of using algorithms to set prices. In repeated pricing games, learning algorithms learn to collude, and these algorithms, these papers have different channels under which they learn to collude. Their results generally show, empirically or theoretically, families of reinforcement learning algorithms find prices that are higher than the competitive prices. I'm going to do something different in this talk. I'm going to show that a family of algorithms that I'll consider good algorithms can easily empirically prove that they are not colluding. Okay? So I'm going to tell you in the future, like in the next couple of slides, what I mean by good algorithms. But these algorithms are not algorithms I consider good algorithms. Okay? In particular, these algorithms are algorithms that are either have explicitly in their model the possibility of colluding, or, and then learn that that's good, or they are making statistical mistakes. And so their sort of ignorance or mistakes results in higher than competitive prices. Okay, and so we'll see why these algorithms in the previous studies I don't consider good algorithms. Okay, so I just want to say a brief couple words on the legal perspective here. This paper is published in a computer science and law conference where understanding the legal perspective is very important. And so you might call algorithmic collusion tacit collusion. We didn't communicate about colluding. We just chose algorithms, and then somehow those algorithms ended up at higher than competitive prices. That's a kind of tacit collusion. It happened, but it wasn't like an explicit communication to collude. Okay, tacit collusion is not illegal, but maybe the existence of these algorithms enables this kind of tacit collusion to a greater extent than before. And so maybe, laws need to be adapted to handle it. One of the reasons why tacit collusion is considered not illegal is that there's this legal perspective of we can't see into the minds of the sellers, and the courts shouldn't be sort of passing judgment on what could or might or might not be in their minds. So if we have explicit communication about pricing, that's just illegal. But if we don't have explicit communication, we don't know what they were thinking and how they got to the prices they got, and so we can't say that that's illegal or not. Okay? What I would like to do today is give you a theory of how to test algorithms that reach higher than competitive prices in a way that says there is nothing in their minds that's consistent with that happening other than, you know, wanting to have algorithms that reach higher prices. Okay? So in other words, the prices we got would not be sort of rationalizable by the cost the sellers have and the information they have. Okay? And so we're going to use those ideas to show that non-collusion is easy to achieve by algorithms, and it's also easy to verify. And so if non-collusion is easy to achieve and easy to verify, then maybe policy can be adapted to require non-colluding algorithms. Okay, and there's a really interesting, you know, when we were working on this paper, I was at Stanford on sabbatical in part, and you know, in the news while I was there is RealPage, this pricing algorithm for apartments that the San Francisco legislature basically tried to pass a law. I don't remember if they succeeded or not, basically saying you can't use algorithms to set prices. You can't. You cannot. Okay, so because of RealPage and the higher prices that resulted from RealPage, the regulators thought that, oh, algorithms are all bad, and we should just not allow people to use algorithms. And as someone whose PhD is in algorithms, I like to have sensible regulations about algorithms. And I don't think of a computer running an algorithm or a person running a heuristic as all that much different. And so I don't feel like you can sensibly just say you can't use algorithms. And so we need a much more sensible definition that allows good algorithms and disallows bad algorithms. And so we're proposing our definition as a replacement for no algorithms, as a much more sensible definition that allows a large family of good algorithms and rules out large families of bad algorithms like the ones in the prior literature. So here's what I'd like to focus on. I don't want to try to say what collusion is. I want to say what collusion is not. Okay? And then I want to have a test where algorithms that are good can easily pass this test to say, hey, look, we were optimizing prices, we didn't collude. That's what I would like. Okay? So I would like algorithms that are colluding not to pass my test. I'd like to be able to just check whether it's satisfied just from the data. And in other words, if I'm regulating that only certain kinds of algorithms can be used, how do I check that those kinds of algorithms are used? Do I say only it's algorithm A, B, or C? These are algorithms you can use? I'm a little bit nervous about that because that harms innovation. You can't come up with a new algorithm D that may be better than these algorithms. Also, maybe you know your marketplace better than whoever developed these algorithms, and maybe some algorithms in your marketplace might be better than these algorithms. So I wouldn't want to say oh, it's only these algorithms. And maybe you're like, oh, well, let's check the source code. That seems like a hard thing for a regulator to do. And moreover, when you run an algorithm, you set the parameters of the algorithm, right? And so maybe some parameters the algorithm is good and some parameters it's not good. So what I really would like to be able to do is just be able to check from data. Okay, so the algorithms keep their data, the regulator keeps the data they need, and we look at the data at the end of the day, do we see, are these algorithms being competitive? So that would be like the best case situation. I don't have to look at source code. I'll let any algorithms pass if their data that they create when they run passes my test. Okay? I would like that if you have a good algorithm, one that gets you lots of payoff as a seller, I'd like that to pass the test. Okay? I'd like you to be able to use very good algorithms. And I'd like it you'd be able to pass the test without sort of sacrificing any performance in any way. In other words, if you have an algorithm that gets some payoff, then maybe there's a way to change your algorithm a little bit so that you get that same payoff or almost the same payoff and you pass the test. Okay? I think of collusion as an agreement between algorithms. And so if you're trying to not collude, that's a unilateral property, right? Anyone should be able to decide, I'm going to not collude. And then no matter what the other algorithms do, you are not colluding because you decided to run a good algorithm that doesn't collude. Right? So not colluding is a very unilateral property. It should be that anyone has the option to not collude. It should not be that someone's like, I'm going to get this guy in trouble by doing this that makes their algorithm collude with me. Okay? And finally, to have a realistic model of collusion, look, sellers all the time have private information about what's happening in their marketplace. If you're talking about Airbnb or Booking.com, then maybe there's a conference or maybe there's a festival and everyone knows that's going to happen this weekend, and so there's going to be more competition, so prices can be higher and everyone can have higher prices and higher payoffs that weekend, right? And so in particular, there could be private information and that private information could be correlated amongst the sellers. So correlation in prices is not collusion, right? Because the demand that they face is potentially, it's all the same customers coming to Airbnb, right? So the demand is correlated, so prices should be correlated. So I'd like a definition that allows the availability of private and public side information. Okay, so here is the definition of non-collusion that I like. And I'm first going to define it as a static equilibrium concept. Okay, so algorithms playing games, that's dynamics, that's complicated. If we can define it for dynamics, we should also be able to define it statically in a single shot game. Okay, and so what I'll call my static definition of non-collusion, and it's going to be a unilateral property. So it's a property just of one of the players in the game, one of the sellers. Okay, so seller 1 is not colluding if their prices are in what I call calibrated best response. Okay, what does that mean? That means given the joint distribution on prices in this static game, and again, there could be correlated information, so the distribution on prices could be correlated in the static version of the game. Okay? When a seller uses price P, conditioned on using price P, P is the best response to whatever anyone else are doing. Right? In other words, the price differences that a seller uses summarizes all information they have about the marketplace, both in terms of what the demand is doing and in terms of what the other sellers are doing. Okay? So calibrated best response says that when a seller is using a price P, then P is the best response, and this holds for every price P the seller uses. Okay, if sometimes the Airbnb host says $100, sometimes they say $120, sometimes they say $150, it better be that of the times they say $100, $100 was the best response to what the market was doing. Of the times they said $120, $120 was the best response for the market, etc. That's calibrated best response. Okay, that's what unilaterally for one seller. What happens if everybody is not colluding by this definition? Everybody's in calibrated best response. That's a correlated equilibrium. Okay, the standard notion of correlated equilibrium. Okay, so my definition of competitive is correlated equilibrium. Okay, I said I want to allow the availability of private and public side information. That means I have to allow correlated equilibrium. And I'm not going to have to allow anything more than that. Okay? Cool. I now want to move this to dynamics. Okay? So if we have dynamics, we have algorithms learning, my notion of the non-collusion is basically we're doing this empirically. And so what does that look like? That looks like calibrated vanishing empirical regret. Meaning, for every price P that you use as you play day after day after day after day, if we go back and look at every time you use price 100, the longer we play, the amount you wish you switched from price 100 to another price in the times you played 100, that regret you have vanishes. And that holds for every price P that you play. Okay? So we want your regret against changing your prices, price P to some other price P prime, price P2 to some other price P2 prime, price P3, etc. Okay, we want that to vanish as time goes along. The longer you play, you learn to be better and better at doing calibrated best response, essentially. Okay, if all sellers satisfy this, then this is the famous result of Foster and Vora. Empirical play converges to a correlated equilibrium. Okay, in other words, we look at the joint distribution of play that results from strategies of all the sellers that have vanishing calibrated regret. And if we uniformly mix over all the days, that distribution over play is a correlated equilibrium. Cool. Okay, so I want to note that in the past studies of colluding algorithms, they find collusion, and in none of them is calibrated vanishing regret satisfied. In none of them. Okay? Moreover, something we're going to see soon is that people in online learning, studying learning algorithms in dynamic environments like this, have many algorithms that are well known to achieve calibrated vanishing regret. So this is an easy thing to achieve. Lots of algorithms achieve it, just not the ones people are studying. That's why I claimed good algorithms can satisfy the definition, bad ones don't. Why do I call them bad algorithms? They don't satisfy those conditions. Well, here's my point. It's kind of like a revealed information idea. When I use different prices, why did I use different prices? Why, as an Airbnb host, when I set a price of 100 one day and 150 another day, why did I use those different prices? Well, that suggests that I have some information. It suggests I have information that says that on the days I used price 100, that was a better price for me. And on the days I used price 150, that was a better price for me. Okay, so I had some information. Okay, calibrated vanishing regret says I have to have actually optimized with respect to the information that I've revealed that I have. I have shown you I can distinguish between those two kinds of days, right? And if I'm a good algorithm, I can do statistics correctly. So I should be able to have vanishing regret on those two sets of days I've revealed that I've been able to tell apart. Okay? Moreover, if you have an algorithm that doesn't satisfy this, it's actually easy to fix it. Like you can take these algorithms that satisfy calibrated vanishing regret and run them on top of one of the other algorithms to fix the calibrated regret, to make it so that it's using its information consistently. Yeah, please.
Imagine I have a player who is not smart,
Yeah.
not optimizing. He's guessing and
Yeah.
having a kind of non-optimal algorithm
would I consider that he's colluding?
So this is going to be a test for non-collusion. I'm not going to tell you what collusion is. And that's on purpose. I can't tell if that guy's colluding or not. It could be that guy call up his friend and be like, hey, it's you and me in this marketplace. Let's use dumb algorithms that just set prices and don't optimize. That's collusion. I can't tell if that happened, so I'm not going to say that's not colluding. But if you want to prove your algorithm is not colluding, you better have vanishing calibrated regret. Okay, think about Airbnb. If Airbnb recommends an algorithm, amongst the people who use that algorithm, Airbnb can then establish that all of them have calibrated vanishing regret, and therefore their algorithm is not price fixing. The other people are doing what they're doing. They didn't use the algorithm. Airbnb is off the hook. Right?
So if I'm testing on Airbnb, I can understand that Airbnb can...
Yeah, let's go on. I've got nothing to say about stupid people. I can't tell you what they're going to do or not going to do. Okay, the other thing I want to say is, as we know, in repeated games, like your repeated pricing games, all kinds of things can happen in equilibrium of the repeated game. Okay? So the Folk theorem says that you can get super competitive prices in equilibrium of the dynamic game. And also there's something in machine learning, looking at policy equilibrium, which is different from vanishing regret. Vanishing regret says, do you regret switching to something in hindsight, assuming everyone else does the exact same thing? So other sellers use the same prices as before. Do you want to change your prices? Of course, in a dynamic game, if you changed your algorithm, other sellers would change what they're doing too. But that's not what vanishing regret says. It says, for the counterfact, for what happened, are you happy? So policy regret is a stronger notion of regret that you could, but it's considering these like repeated game concepts. Okay? And here's the thing. These Folk theorem results are exactly things like, tit for tat or whatever, things that you want to exclude if you want to regulate people not to collude. Right? Those equilibria in the dynamic game, that whatever they are, that these are the ones that have higher prices than the competitive prices. So what we're sort of recommending here is the regulator check the data to force algorithms in dynamics into a stage game equilibrium of correlated equilibria and not let them play equilibria of the repeated game. Okay? We can check the data to enforce that they are not playing equilibria that are outside the equilibria of the stage game. And that's really what we mean by competitive. Competitive equilibria are equilibrium of just the, the market scenario, and not equilibrium of some kind of tit for tat thing, long run play of I keep the price high if you keep the price high, right? It's exactly the thing we want to exclude. Cool. So what is my, so look, I'm a theorist, and I write papers that have theorems in them. And so I want to tell you what the main, so far it's mostly like modeling, right? It's like, how do you think about this? Right, so what are the theorems in the paper? So let's suppose we want to empirically audit non-collusion. I want a test that tells me, is this algorithm colluding or is this algorithm not colluding? The main question that you get to if you're doing statistics like this is how much data do you need before you can be convinced that someone's not colluding? So that's going to look like a situation kind of like this. Okay, so regret is going to hopefully vanish in the long run, but I can't regulate people at infinity. I have to regulate a finite amount of data, right? So I'm going to set a target amount of regret I will allow, R bar, okay? And a failure probability delta. This is the probability I allow my test to be inaccurate, okay? And I'll define the sample complexity of empirical non-collusion audit is T the number of steps I need as a function of the regret I want and the failure probability I allow, so that if the calibrated regret is at most r bar, then we pass with probably at least 1 minus delta. So with high probability, we pass the test when we should pass the test. The player has low calibrated regret. Okay? And if the calibrated regret is at least twice r bar, so much bigger than r bound, then we're going to fail with high probability. With probably 1 minus delta, they fail the test. And so my question is, how much data do I need for this to happen? Okay? And so let's then figure out, let's specify some of the details of the environment. And so imagine we have an environment and a pricing algorithm where the pricing algorithm is going to use one of k discrete prices. So in Airbnb, maybe it's 100, 110, 120, whatever. Whatever your market is, there's going to be some number of prices you allow the algorithms to use. Okay, let's let the highest price be p upper bar. Okay, and let's assume that my algorithm is going to do some experiments as it runs. And when it does experiments, the minimum probability of choosing any action is some small number pi lower bar, like maybe 0.001 or something. Okay, with some small probability, you pick a random action. Okay, so if this is the situation, then there is an algorithm that tests this empirical regret that has this probability when the number of rounds it runs for is at least, and here I have some crazy math that you should be looking at going, why do you write that crazy formula on the board? And I don't usually like to read crazy formulas, but it tells you the dependence on all of my parameters. Okay, look, so if you have more prices, the dependence, it looks like k squared. Okay, as you decrease the exploration probability is like 1 over pi squared. Okay, and that's the usual law of large numbers, right? That you need to get like low variance on something. So you expect it to be something like squared, and we get that. Okay, so you could expect my formula and see what the dependence is on any of the parameters if you want. Otherwise, it's a number. Cool. I want to say a brief word. Okay, so these slides look very similar, so I'm going to go back. This was my slide. And watch this area. Boom. Here's another problem. If we're the regulator, we don't necessarily know the true cost of the sellers. So we're going to do econometrics at the same time as we do this. So what we'd like is that, again, and we're going to use this idea that we can't see into the minds of the sellers. So if there exists a cost where for that cost the seller has vanishing calibrated regret, the seller is good. I can't see into their minds. So if there is a cost for which their regret vanishes, looks good. Okay? On the other hand, if the calibrated regret doesn't vanish for all costs, it's all high for all costs, there are no situations in which that is a good algorithm. Okay? So basically what I'm saying is we're going to do reveal, so calibrated regret is like revealed preference for information. I look at the actions you choose, I look at the information you reveal you have by choosing different prices, calibrated regret. We're also going to do revealed preference on costs. Okay? And so if there exists information and there exists costs for which what you did was good, then you're a good algorithm. If there does not exist information and cost for what you did is good, then we exclude your algorithm. We don't pass your algorithm. Cool. I have 15 minutes left in this presentation. Basically, I've told you like all of the new stuff of the paper. Everything new I told of the paper. And so the remaining 15 minutes, I want to go a little bit into some of the algorithms and that are in the literature and how you think about this thing so that you can understand how regulating algorithms looks like in environments like this. Okay? And we'll get as far as we get in the 15 minutes. If you attended the winter school last week, the first lecture, Nicole's lecture, talked a lot about regret, multi-arm bandit, propensity scoring, etc. Here we're going to introduce this idea of calibration and cost inference over what Nicole talked about last week. Cool. So let's, again, I want to introduce this idea of algorithms that have vanishing regret. So let's just start with a toy problem, which is just one seller and nature. Okay? The seller is trying to learn to use a high and low price, and nature is choosing the buyer's value to be high or low, the demand. Okay? And here's the point. If I'm regulating just one player's vanishing regret, I don't care if the demand comes just from nature or comes from competing sellers. It does not matter to me. Right? As the seller uses higher and higher prices, the demand goes down, regardless of whether that's because the buyers had lower values or they chose to buy from the other seller. Right? So I don't actually, so this is like enough for me to think about everything. I just don't care where the demand comes from. I'm going to use an algorithm to learn the demand, regardless of where it comes from. Cool. So the seller is going to have a low price or high price. Nature is going to choose low or high value. If we use a low price, then for any value of nature, we make a profit of the low price, a quarter. Okay? If we use a high price, then if nature has a low value, we get 0 because the buyer doesn't buy. If the nature has a high value, the buyer has a high value, then they buy and we get 1. Okay, so that's a very simple model to look at an example. Okay, and this is basically like dynamic monopoly pricing now because I have just nature and a buyer, but if we were in competition, it'd be dynamic competition. Okay, so now I can say, let's imagine that nature chose the following situation, low, high, low, etc. And let's imagine our algorithm chose the following, high price, high, etc. I'm not saying why, but let's imagine that happened, and let's think about what we were doing. Okay, so I can now think like at the seller, like they chose a high price, but let's just keep track of what would have happened counterfactually for any price. Okay, so had they used a low price, we had a buyer with a low value, and so the low price gets a quarter, high price gets 0. Here we have a buyer with a high value, so low price gets a quarter, high price gets 1. High value, quarter 1. Low value, quarter 0. Low value, quarter 0. You see what I'm doing? I'm just filling in the payoffs that we would get for any choice of the seller given nature. Okay? So now like this doesn't really matter too much. All that matters is actually the payoffs I get for the actions. Right? I got that from this and this, the data generating model, but all that matters is these payoffs. Cool. Okay, so summarizing this table, what if we just offered a low price the whole time? Well, you get a quarter all the time. Our average payoff is a quarter. If we offer the high price the whole time, well, half the time it's 1, half it's 0. So the average payoff for a high price is a half. So in hindsight, we really would prefer just to offer a high price the whole time. What did our algorithm do? Our algorithm did high, low, etc. I think I have an animation for this. So yeah, that's the low price. That's the high price. And the algorithm did this. So we could sum that up and average it, and we'll get 3/8. Okay? And so the regret in hindsight is the best of these two, best in hindsight. Okay, so best in hindsight is the action with the best average payoff in hindsight. So that'd be the high price in this case. And the average regret is the average best in hindsight payoff minus the average algorithm payoff. Okay, so that's going to be 1/8 here. It's a quarter minus 3/8. Okay. In this pricing game, though, our algorithm, typically you post a price, you see if someone buys or not, but you don't see like what would have happened had you posted a different price. So our algorithm basically sees this. And that's what's called multi-arm bandit feedback. We only see the payoff of the actions we took. We don't necessarily see the payoff of other actions. Okay, and so like if I'm a seller in Airbnb, I use a price of 100. Maybe someone books my room. Do I know that no one would have booked my room if I'd used a price of 120 or a price of 150? Maybe someone would have booked my room then. I don't know. Cool, so that's multi-arm bandit feedback. So let's go into a little bit more detail into the multi-arm bandit model. This is a fundamental model in online learning. I have a bunch of actions. I play a bunch of rounds. In each round, there are some payoffs that come from nature, which are what I wrote in my table, U1 for action 1 and UK for action K at time t. And our algorithm is going to make some randomized choice, pi t, which is a distribution over all of the actions. Okay, its expected payoff is just the product of the probability of choosing the action and the payoff it got. Of course, it realizes a choice. And so it actually is going to draw some JT from the distribution pi t. And it's going to learn only the payoff of the JT that it chose. Okay? And it's going to receive that actual payoff. Okay, this is the actual payoff. This is the expected payoff. But it only knows this. Okay, so the best in hindsight payoff is just the max over all actions j of choosing j in every single round. Okay, the algorithm's realized payoff is the sum over rounds of the action of the payoff it got. Okay, its expected payoff is sort of the same thing, but using the expectation according to the distribution it knows it chose. Okay, and we can write out its average regret as the difference between choosing the best action in hindsight and the expected payoff it got. Okay, so there's an amazing, awesome literature developing algorithms beginning with this 1995 paper in Fox. There exist algorithms with vanishing average regret as t goes to infinity, even against adversarial inputs, even against nature working against you, trying to make your regret big. Okay, I'm not going to obviously talk about these algorithms, but the main ideas in these algorithms are we have to do counterfactual estimation to get payoffs of actions we didn't choose. And so we're going to use propensity scoring for that. I'll talk about that a little bit on the next slide. Because of that, we're going to have to do some exploration, or we're going to have to, actions we never played, we can't learn are good. So we better play all actions with some little probability. Okay, and to work against adversarial inputs, we shouldn't always choose the thing that looks best in hindsight. We should actually perturb it. So if a couple of things look pretty good in hindsight, let's just randomize over things that are nearly as good payoff in hindsight. Okay, so use a soft max, follow the leader style approach. Okay, those are the main ideas that go into making theorems like this hold. Good, let's talk about propensity scoring. So we have multi-arm bandit feedback, which means we chose action j in round t, and we only learned its payoff. We did not learn the other action's payoff. But in order to have this low regret property, we better know if other actions are good. Okay? So the main approach is to explore. So we ensure the probability of each action j is not too small. So we want to keep pi jt at least some pi lower bar. And then we'll do propensity scoring. We'll use an unbiased estimator defined this way, which is an unbiased estimator for the true payoffs. In other words, if I did choose action j, I'm going to put as payoff the payoff I got divided by the probability that I chose those actions. So in expectation, I get this times the probability, so the probabilities cancel, I get this. Okay, I put in 0 otherwise, and so in expectation, these estimates are equal to the true estimates. Okay, and it turns out these online learning algorithms are robust to unbiased estimates. They don't care. If you put in the real payoffs or you put up payoffs with the same expectation, doesn't matter to them. They'll learn anyway. Okay, here I just did the calculation. It's an unbiased estimate. Cool. So there's an explore-exploit trade-off, because if I let this probability pi lower bar be too small, then it's going to be in the denominator here, 1 over that, right? Which then blows up this term, which makes the variance of my estimates super high. Okay? And that if my estimates have super high variance, that makes my decisions bad. And so I need to balance the trade-off of the high variance and exploring actions that have low payoff. Okay, sellers may have side information, and side information may be correlated. So here we're talking about calibration. And the idea here that I think is just super fascinating is that side information that was useful is revealed in the choice of different prices. If you have information but then use the same price, you didn't need the information. Wasn't helpful. Use the same price for both pieces of information. Okay? So if you have useful side information, that's going to be revealed in choosing different prices. And I see the prices so I know exactly when you have that useful information. Okay? So calibration is basically saying the prices are calibrated for any price P. For the times we played price P, P was the highest average payoff in hindsight. Okay? And there's an amazing paper by Blum and Mansour that shows if you have an algorithm that achieves vanishing hindsight regret, like we talked about in the first slide, against like one action, you can convert that into an algorithm that has vanishing calibrated regret. Okay? And it's just a black box reduction that does this conversion, and it's really brilliant paper. If you haven't seen this paper, definitely read this paper. Okay, the last ingredient in this puzzle. I got 1 minute.
Okay.
Do you want to ask your question? Perfect. Is that I need to infer costs. I might not know the cost of the sellers, and so I need to infer the costs. Okay? And so let me just remind you the utilities in the pricing game. The utility of a seller is price minus cost times whether or not the buyer bought at that price. Okay? Good, looks like that. So Nick Appella et al. Had this amazing paper that said, you know, we'd like in econometrics to do structural inference from equilibrium, but it turns out the no regret property is just as good as doing structural inference. Okay, so if we write out the no regret condition, it looks like this. We have an inequality for every so this equation says the following. Here are the things we don't know. We don't know what the seller's actual regret is, and we don't know what their real cost is. So I put those in as variables. Okay? And then I want to write the equation that the regret is more than what we saw in the algorithm for looking at using price J, a single price J, versus using the price J the algorithm took you. So the algorithm uses price JT, and we're comparing that using any single price J. Okay? So in my data, I have all of the information except the red. This is a linear equation except in the red variables. So it's a linear equation in the red variables, so it looks like just half spaces, right? And so what we're saying is the regret has to be, you know, above here for each of these costs. Okay? And then the idea is, well, I want to say there exists a cost with low regret. That's exactly this point. Okay? That's the cost that gives me the regret that looks the lowest for the data that I have. Okay, so the condition that I'm trying to check my data for is, when I look at all the stuff that's happening, is this thing below some R bar, and as I get more and more data, I get more and more confident these estimates get better. I get more and more confident in whether that's below some line or bar. Okay, so this was my definition of non-collusion. This is also my last slide. And so rather than talk about it again, you can look at it and Rita can ask me a question.
Let me. So first, let's thank Jason. And I'm going perhaps to see if there are any person connected, because we have how many people are connected? 11. So if anyone. Yes. Okay. So can you, if you have questions for people that are connected, can you please write your questions? Il écrit? Nothing? You can perhaps write the question, because I'm not sure that they're hearing us. Everybody's hearing the presentations? Okay. So let's ask questions from the audience. Okay, good.
So now the algorithms will go through a non-collusion test, right? Non-collusion. If they pass, then that's good. If they fail, so do we judge them colluding algorithms?
Yeah, so look, Rita asked me a question like, what about dumb sellers who don't know what they're doing and just post prices and don't think about it? So I can't tell dumb sellers from sellers who are colluding on high prices with this test. I can't tell them apart. Okay, so what I would say is that sellers that pass this algorithm, if eBay wants to have, like, publish an algorithm, this is good, because now eBay can know that they're going to be in good shape, that they can pass a test to prove that they didn't collude. Now, a seller, like if you're in a marketplace, you know, like San Francisco with the rental housing, instead of saying no algorithms, you could say, if you use an algorithm, better pass this test. So then I rule out algorithms other than these kinds of algorithms. I still allow innovation because many algorithms satisfy this test, but I don't rule out all algorithms. And if San Francisco thinks that they can rule out all algorithms, then they can certainly rule out all algorithms except the ones that pass this test. Okay, so that's what I would say about this. Exactly.
Rémi.
So I was thinking about the app in Drive. I don't know if you used it here, where the app proposes a price to the customer, and then the customer can use this price or decide to use another one. So obviously the app has an incentive to propose higher prices because I guess they have a commission. But so in this sense they can fix the price, but so it looks like collusion, but it's not. They don't propose the price to the sellers, they propose the price to the customer, so the customer can always try to get a lower price. So would there be a definition of collusion? Would you define this as collusion?
That's a very interesting question. If you look at Uber instead of InDrive, they don't even let you propose a price. They just set the price, and everyone uses that price. And now, in some sense, Uber and Lyft are in competition for the prices, but not the sellers. The sellers aren't really in competition, right? I think it's easy to imagine trying to look at the data to see if it passes this test, but then I think you would have to ask yourself what you thought about it.
You still have to take into consideration that they give you a range for the price. They set a threshold from which you can't go any lower.
Yeah.
You can go below the in-drive prices, can't you?
Yes, you can go
Can.
below the proposed price, but there is a threshold
Ah,
that you
there's-
cannot
Which
go.
you can-
Hmm.
So even if you're impacting this, you can't implement it in a way that will harm in-drive.
Probably that's because indirect doesn't want you to have the fraud.
You say, hey, look, I put in a low price. That means we can negotiate when you get here, and we'll pay in-drive a very little bit, and we'll have a long ride. It's a good question. Getting in-drive's data would be amazing.
Can try to buy it.
So now I'm thinking of Uber because in France, for instance, Uber has almost a monopoly on this kind of services. And so, would you say that Uber is price fixing? Because I mean, I don't see why they would not do it, and I don't know if there is a law against it. So, do you think that they are price fixing, or do you think that they are using equilibrium prices?
Well, monopolists are not in competition. I wouldn't call that price fixing. I would call that monopoly pricing. And if you're a regulator considering a monopolist, then you would consider them in that setting rather than in the competitive setting, right? And in that setting, you would say, look, maybe ride sharing is a natural monopoly because if you don't have any customers, you're not going to get any riders, right? And if you don't have any riders, you're not going to get any customers. So how can someone come in and compete with Uber? And so then maybe the regulator might want to do something to set the prices, to constrain the prices Uber is allowed to use, which is typically what happens in a natural monopoly, right? I might take that perspective. It's interesting to suggest that one way around this monopoly of Uber would be to require Uber to let the sellers choose the drivers or riders even choose their own price with or without the recommendation of Uber.
Okay.
That's a great question.
So,
There was another question joining Rivi's question.
yeah.
They said, how about the MRP, manufacturer reference price? Example, graphic cards during the era of mining.
Can you repeat the question again?
So the question is, how about the MRP, manufacturer reference price? Example, graphic cards during the area of mining.
Yeah, so I guess the question is about GPUs for Bitcoin mining. And when a manufacturer makes a product, the manufacturer might list a price as what they think is a good price for that market, that commodity, and then many different storefronts might sell the thing at that price. And the question is I guess, is that price fixing by the producer of that commodity? I don't really think of that as price fixing either, because we need to think about how the retailers and the manufacturer are integrated, and under, and I guess ask, what do what the retailers are doing is competing with each other for the one that you'd want to go to. Like maybe you buy it on Amazon, or maybe you buy it at a brick and mortar store. In this space of sort of list price and these different retailers, I think one of the things that I really like analysis that Kamal Jain, formerly at Microsoft, who then went to Amazon, did of this, saying that, if you're running a brick and mortar store, maybe your costs are a lot higher than these online retailers. And so having them compete on price is maybe a problem. But the entity that makes money regardless of where you buy from is the manufacturer, right? You manufacture these GPUs, right? And if you buy them on Amazon, you buy them at a brick and mortar store, you buy them anywhere, the manufacturer makes the money, right? So maybe the manufacturer should be subsidizing the brick and mortar stores so that, and the example that Kamal Jain gave was like designer jeans or eyeglasses, right? Eyeglasses are very much more expensive in the stores, but what prevents you from going to the store, trying them on, finding the one you like, and then going online and ordering it? Now the store is paid to stay open so that you could have that experience, but they're not getting the money from buying it. And the idea that Kamal Jain had is that the manufacturer should be paying the retail stores to stock the item, you know, at eye level, where lots of people see it and be like, oh, I like those glasses or those jeans, right? And it's kind of like, you know, advertising on the internet where, you know, you pay to have your ad shown up, and then, so like the manufacturer pays the merchant to show the item, and just then if you make the sale, nobody cares where it goes from. It goes back to the manufacturer, the money. And so then I wouldn't view that as competition. But these are great questions.
Good. So I think, I'm sorry, we need to stop at some moment. And we would like to thank again Jason, and waiting for your next talk next year.